The final example for this lesson is we're going to try to use these slope fields to construct solutions to these two differential equations in by approximating them, rather than often it's not feasible or even possible to find an exact solution or what's called an analytical solution by solving it. But what we can do is, using the differential equation, we can approximate points along a solution curve. The most probably famous method for this was developed by Euler, and it's called his method of numerical integration. There's a picture of the process here, and it's an iterative process, meaning we're going to use the same kind of formula, the same algorithm over repeatedly until we end up at our approximated solution. So here's a picture of kind of what's going to go on, and I'm going to kind of talk through what this picture is trying to say. So what we're trying to do is we have some slope field going on in the background. We don't know but we don't know exactly what this curve is. What we do know is that we have a rule for the function for this differential equation, and we know an initial value. We know a coordinate that's definitely on this solution. Call it x naught and y naught, which is represented here. So Euler's thought for how can I do my best to follow what the curve should be or will be is the following. He starts with we start at this coordinate x naught, and then we're going to get successive new coordinates in this way. We're going to start by taking our initial x coordinate. We're going to add a little bit of the step. In this case, we're using the symbol h for this. This is called the step size. And this will always be, if you're asked to approximate using this method, you'll be told what the step size is. In fact, if you look ahead in this example, it tells the step size is 0.2. But this is something you'll choose ahead of time, or it'll be told to you what it should be, what you should use. So in order to get, what Euler's thought was to get the first approximate x value, or x1, we're going to take the old x value, or the previous one, in this case x naught, and we're going to add whatever the step size was. To get the first y approximation, well, how do we come up with if we move some step to the right, how far up do you go? Well, where you'll end up at is wherever you started. You'll take wherever you start at, and then we're going to add kind of the y part of this little triangle that we make. So note that the x part is we've walked h to the right. So how far up do you go? Well, how far up you'll go is you're going to follow this tangent line, which is the slope of the tangent, which is the value of the slope field at this point, or the value of the derivative at the original point, 0 x0 y0. And then we're going to use this slope, and we're going to go this distance h. So what we're going to do is we're going to use the value of the derivative at the previous spot. So dy, I'm going to use this symbol, dy dx at the initial value. My computer is erasing for some reason. At the initial value, x naught, y naught. And then we're going to multiply by how far we walked. In this case, that's the step size. So that's times h. And when we do that, we'll end up at a new y coordinate, which is x1, y1. To get the next point, we're going to repeat this process. So to get the second x coordinate, we're going to take wherever we were at just before. We're going to add the step size again. To get the second y, well, we're going to repeat this process. We're going to take where we were at just before, which is the previous y coordinate. And then we're going to add the derivative at this, the derivative of our, or the value of the slope field, or dy dx, at the previous point, at x1, y1. And again, multiply by the step size, because that's how far we're going to walk along this way. Then it gets to the second point. And then we can keep going until you end up at, until you get to, if you want to do this n times or whatever, until you get to the y value, to the x value you're looking for. Then you can find the y value you would be at. This will make more sense if we do this, if we actually work on a problem. But we're going to use the same kind of idea. So here's a specific differential equation. Suppose here's the differential equation, dy dx equals x plus y. And this initial condition is true. So we know that when x is 0, y is 1. So we're going to use this method with step size of 0.2, or h is 0.2. And we're going to try to figure out what the value of y of 1 is, meaning we're going to stop once our value for x is 1. So we're going to we'll start by making a table here that we had. So let's see. I know that x naught is 0, and I know that y naught is 1. Okay, so I know. Let's get our first step. I know that x1 should be x naught plus 0.2, which is unsurprisingly 0.2. I know our first y should be the previous y, which is 1, plus now the value of the derivative at the previous spot. So the value of the derivative when I'm at 0, 1. Well, the derivative's value is x plus y. So this should be, so the value of the derivative at the previous spot is 0 plus 1. And I'll multiply by the step size. 0 plus 1 is 1. 1 times 0.2 is 0.2. This happens to be 1.02, or 1.2. So 1.2. Okay. Repeat. The second step is going to be the previous x plus the step size. The second y should be the previous y plus now the value of the derivative at the previous location at x1, y1. And again, our formula for the derivative is, well, for this particular differential equation is just take the x and add the y. So in this case, our value of dy dx is 0.2 plus 1.2, because that was the previous y. This is the value of the derivative of the previous spot, and I'll multiply again by the step size. And if I type this in my calculator, I get the value of 1.48. I'm going to continue this process until the x coordinate is equal to 1. So let's do it a couple more times, and it shouldn't be 2. I think 3 more. I think we need 3 more times. 3 is 0.6. y3 is 1.48 plus again the sum of x and y at the previous step, which is 0.4 plus 1.48, and multiply that by the step size. And again, type that in my calculator, and I find that that is 1.856. Oops, that's kind of awkward, but it's okay. Okay, 2 more steps. The fourth x is the previous x plus the step size, which is in this case 0.8. The fourth y is the previous y, 0.856, plus the value of the differential equation at the previous spot, which is again x plus y. So 0.6 plus 1.856 times step size, which by my calculation is 2.3472. And it looks like lastly, this will be the last step because I'm going to take, when I add the step size again, now I'm going to get exactly at the x value I want to approximate, which is x equals 1. 0.8 plus 0.2 is 1. This is the fifth step. So the fifth step, I actually get to the x value I want, and so that tells me that this will be the last y value I need to calculate. So the fifth y is the previous y, 2.3472 plus the value of the differential equation, which is at the previous step, which is x plus y, times the step size, which is 2.9766. And then if this were the IB exam, I'd round to 3 sig figs, which is in this case would be the first 3, which would be 2.98. For the AP exam, I went to the third decimal place, so I think this should be the value. How about the value of y1 is approximately, to the third decimal place, 2.977.